Hello guys, so let's continue. Today we have a very interesting lecture and there will be almost no linear algebra in that whatsoever. So this is lecture 11. 1 second. Yep. Lecture 11. And we will talk about permutations. Okay, so definition is very simple. So a permutation is a bijection from the set one, two, and so on, n. This is just a set with n elements to itself. So of course it is not important how we label the elements, it is just important how many of them we have, and usually people denote this set by n in brackets. So okay, so typical example of permutation is a map from the set n to itself. And of course it's enough to say what goes where. So for instance, if n equals to 3, then typical permutation is something like sigma 1 equals to 3, sigma of 2 equals to 1, sigma of 3 equals to 2. Okay, so there are two, or actually more, but we will talk about two convenient ways to denote permutations. So suppose we have a sigma. This is a permutation. Then one can draw it in the following way. So one can just write down sigma as, and then in brackets, kind of a matrix, where in the first row you have all the elements from 1 to n, and in the second row where they go, like sigma of 1, sigma of 2, and so on, sigma of n. So for instance, this one was just sigma equals to 1 goes to 3, 2 goes to 1, and 3 goes to 2. That's an example. So okay, another convenient way to denote them is to actually draw some picture. So sometimes it is convenient to draw the corresponding arrows connecting a number here and where it goes. We know it's a bijection, so definitely, 3, 1, 2, 3, 1, 2, and then we have a graph like that. So we will later talk about such diagrams and why they are important, but also one can think of permutation as this sort of sequence of arrows, so that for every arrow here it goes somewhere downstairs, and it is a bijection. Perfect. So okay, so the set of permutations is denoted by Sn, and it is very easy to compute the number of permutations. So the size of the set of permutations equals to n factorial. So the reason is that actually if you have n elements and you want to permute them, you need first to understand where to send 1, and you have n options. Then after that you need to send somewhere 2, and you have n minus 1 options for that, and so on. So in totality you have n times n minus 1 times and so on times 1. So probably you have seen it already somewhere. That's a very standard elementary set theory observation. And for instance, if you have n equal to 3, I can just write all of them down. So I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 1, 3, 1, 2, 3, 1, 3, 2, 1, 2, 3, 3, 2, 1, 1, 2, 3, 2, 3, 1, and finally 1, 2, 3, 3, 1, 2. That's all. Okay, so what can we do with permutations? So for every permutations sigma and tau, we have a new permutation sigma times tau. So this is a product, but what it actually is, it is just a composition. And it is defined by the rule that for every I inside the set, which is defined sigma tau of n as first you do tau, and then you do sigma. So basically, with permutations, there is one operation you can do with them. That's called multiplication. But also, and this is as usual a map from Sn times Sn to Sn, but also it is just a usual composition of maps. So also, if you have a permutation sigma in Sn, then you have sigma inverse is also inside Sn, and this is just a bijection backwards. So let's look at some examples. Okay guys, so let's compute a few examples of these compositions. So let's take, for instance, n equal to something interesting, which will be, say, 6. And then we have two permutations, sigma and tau, inside S6. And we can imagine that sigma, for instance, equals to 1, 2, 3, 4, 5. 6 goes to 2, 1, 4, 5, 3, 6. And say tau is 1, 2, 3, 4, 5, 6 goes to 2, 3, 4, 5, 6, 1. So then I can compute tau sigma, for instance. And for this, I first do sigma with some number and then do tau. So 1 goes to 2, 2 goes to 3, 2 goes to 1, 1 goes to 2, 3 goes to 4, 4 goes to 5, 4 goes to 5, 5 goes to 6, 5 goes to 3, 3 goes to 4, and 6 goes to 6, 6 goes to 1. But I can also compute their composition in other order. And then I first need to start with sigma, with tau. So 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 4, 3 goes to 4, 4 goes to 3, 4 goes to 5, 5 goes to 3, 4 goes to 5, 5 goes to 3, 3 goes to 4, 4 goes to 5, I'm sorry, 5 goes to 6, 6 goes to 6, and 6 goes to 1, 1 goes to 2. And notice that sigma tau is not equal to tau sigma, so order actually matters. And if I want to compute, say, sigma inverse, that's also not very hard. I just need to, okay, I can see that 1 goes to 2, 2 goes to 1, so I just read it from bottom to top. 3 goes to 5, so 3 goes to 5, 4 goes to 3, 5 goes to 4, and 6 goes to 6. Okay, so hopefully I convinced you that multiplication, taking inverse and so on is easy for permutations. Okay, so what properties do these operations have? So the main idea is that permutations form a group. So, okay, so I know this is terrible. You have never seen abstract structures before, probably, and now you see so many of them. So we already had a field, an abstract vector space, we had a ring of polynomials over a field, we had rings, and so on and so forth. So this is another one of the same types. That's what's called a group. Let me define that. So definition is as follows. So a group G is a set, which is also called G, and a map from G times G to G, which is called multiplications, if you wish. So if you have two elements, G1, G2, what you do with them, you just kind of multiply them, and this is how people write it, such that And then, so remember, we had different operations like in a field and in a ring, and we just need to write down all properties which hold for multiplication, so everything which depends on one operation. So first, for every three elements G1, G2, G3, in G, we have that G1, G2, G3 equals to G1, G2, G3. Associativity. So multiplication is associative. Second is that there exists an element which is usually called E, which is also denoted by 1 sometimes, such that for every G in G, G times 1 is 1 times G is G. Identity. Again, we have seen it already. And finally, 3 is inverse. So for every element G in G, there exists the one which is called the G inverse in G, such that G inverse is equal to this E, or 1, if you wish. So that's it. And we have already seen a lot of examples. So let me just show you a few. So for instance, you can take, so we need a set and operation. So for instance, you can take like integers and addition. You can, and then of course all properties are satisfied. And then you can of course take actually any field and addition. Also subtraction will be this inverse and 0 will be this 1. Also you can take any vector space V, sorry, any vector space V and addition. That also works. But this is all boring, especially because everywhere here we have the properties that G1, G2 equals to G1, G2, G1, so the order does not matter. And this is called commutativity, and this is not true in all groups, so that's not required. And here it's true, so these are very simple examples. Another example is you can take a field without 0 element and multiplication. So then that's a little bit more interesting where this is a field, because in a field you know that you can divide on everything except 0, and so if you take f without 0 you get a group. Okay, but there are more interesting examples. So actually a really interesting example is Sn. That's the most important group, and notice it is finite, so it has n factorial permutations, and the operation is of course this composition, which we just discussed. Here is an inverse, and this identity is just a permutation. 1 goes to 1, 2 goes to 2, and so on, n goes to n. And finally, there is another interesting example of a group. So you can take f some field, and then you can take a group. So group is denoted by gln of f. This is a group invertible matrices. So these are matrices A inside n by n matrices, such that there exists a inverse. So, and of course operation is that if you have A, B, two matrices, you can invert the product, and the product is just B inverse A inverse. So product of invertible matrices is invertible. So that's very interesting group, and these two are actually the most important examples of groups in mathematics, arguably. And if you study finite groups in Algebra 1 course, you will mostly think about this one and various relations with other stuff. But if you do more advanced mathematics, if you go to things like representation theory, you basically study this one. And these two groups are related in a very interesting ways, in many different ways actually. So that's where amazing mathematics actually starts. And but this is both groups we can define, so we will need this one today, and this one we already saw. So matrices, invertible matrices, that's the same as isomorphisms from a space to itself. So in some senses groups are a little bit similar, because these are bijections from a set of an element to itself, and these are isomorphisms from a vector space of dimension n to itself, and so you can think of them as kind of similar or at least related groups. Perfect. So what is our next plan? So I will talk a little bit more about these permutations, and later today we'll talk about the most important property of permutations, namely sign. Actually, all permutations can be divided into two types, even and odd, and this is very important for us. And by the way, you may wonder why I'm talking about that at all. So later on we will talk about determinant, which is a formula to understand whether a matrix is invertible or not. And this formula uses these permutations essentially, so it's a very beautiful formula, and to just write it down I need to talk about this stuff. Also, I think it's amazingly beautiful, so why don't we have a break from vector spaces and vectors. Okay, now I want to talk a little bit about transpositions. So transpositions. So a permutation, so a transposition ij inside Sn is a permutation sigma such that, so sigma of k equals to k for k not equal to I or j, sigma of I is equal to j, sigma of j is equal to I. So basically what it does, it takes your elements from 1 to n, and I and j are just exchanged. So you basically exchange two elements, I and j, everything else stay fixed. So for instance, in S3, there are three transpositions. 1, 2, 3 goes to 2, 1, 3, which exchanges 1 and 2 in places. 1, 2, 3 goes to 1, 3, 2, which exchanges 3 and 2. And 1, 2, 3 goes to 3, 2, 1, which exchanges 1 and 3. And in general, it's very easy to see that the number of transpositions equals to number of pairs, so something like n times n minus 1 over 2, I guess. So that's a natural idea. So here is a very important theorem, which is easy but important. Every permutation sigma in Sn is a product of transpositions. So what it means that basically if you have a permutation sigma, then you can write it down as a product T1, T2, and so on, Tk, where this T1 and so on, Tk are transpositions. Okay, so what it means intuitively? Intuitively, it's a very naive idea. So imagine you have a set, and imagine your set consists of a few rhinos. So that's a rhino, 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 and they have some names like 1, 2, 3, 4. And you want to exchange these guys, just exchange their order in some way. And you know that what you want eventually, you want something like 4, 3, 2, 1, for instance. So you want this guy to go here, this guy to go here, this guy to go here, and this guy to go here. And of course you can say, okay, rhinos, let's just run, and then they start running and probably crash into each other, and this is terrible. So that's not how we do it. How we do it is we take first two rhinos, and then we exchange them maybe. Then we exchange some other rhinos, and then we just continue asking a pair of rhinos to exchange their places until we get to this position. And the theorem tells you that you can do that. So let's see how to do it here. So of course, the first thing we will do is let's just exchange 1 and 4. So we had a permutation 1, 2, 3, 4, and then let's just exchange 1 and 4, and then we get 4, 2, 3, 1. So we got a transposition 1, 4 applied at first. So why this is good? Because we want 4 eventually go to 1, and now 4 already goes to 1. So we just need to check what happens with 1, 2, and 3. Okay, so we want 3 to go to 2. Sorry, 1, 2, 3, 4. Yeah, 1 goes to 4. This is what I mean. Yeah. So then we want 1 goes to 4 now. So then we want to see what happens to 2. So 2 should go to 3. And now 2 goes to 2. So let's exchange 2 and 3, and then when we do that, we get a permutation 1, 2, 3, 4 goes to 4, 3, 2, 1, and 3, 2. And now we know that 1 goes to 4, 2 goes to 3, 3 goes to 2, 4 goes to 1. So this is exactly what we want. And so what we got is that our original permutation 1, 2, 3, 4 goes to 4, 3, 2, 1 is the product of these two transpositions. So, and of course there are many ways to write it down as a product of transpositions. In particular, because if you have any transposition ij, then clearly ij squared equals to 1, because if you just do it twice, you get that nothing changes. And so, for instance, you can take this product and plug in somewhere 1, 2 squared. That doesn't change anything. So that's the idea, but of course, let's prove it rigorously. Okay, so proof. So assume not. So let f of sigma, so sigma is some permutation. So let f of sigma be the biggest, the largest k from 1 to n, such that sigma of k is not equal to k. So, so basically, what do I mean by that? So when you take your permutation 1, 2, and so on up to f of sigma, so this guys here you get. So this is largest number. So this one is not equal to f of sigma. And after that, you have f of sigma plus 1. This already goes to f of sigma plus 1, and so on, up to n goes to n. So basically, after f of sigma, the permutation just does nothing, and before f of sigma, it does something, so it changes stuff. So, sorry, and be the largest number from 1 to k. Yeah. So if such number does not exist, put this f of sigma equal to 0, just formally speaking. And of course, this happens if and only if sigma is just our identity permutation. So 1 goes to 1, 2 goes to 2, and so on, and goes to n. Perfect. And as usual, so the idea is that let's take the counterexample, the permutation we cannot present as such a product, which has the smallest such f of sigma, and then make it even smaller. So that's the idea. And so here it corresponds to the fact that first you do some transpositions to send n to n, then to send n to n, and n minus 1 to n minus 1, and so on and so forth. So let sigma be a counterexample. So counterexample to the statement, meaning a permutation which is not a product of transpositions with smallest f of sigma. So if f of sigma is equal to 0, then it means that as we agreed, so such number does not exist. So it just means that it just means that that everything goes to the same number. So our sigma is just 1, and 1 is definitely so this is a product of transpositions, and you can think of it as either just no transpositions at all, or you can think of it as you can take any transposition and take a square and you get 1, for instance. So that's clearly a product of transpositions. So so f of sigma cannot equal to 1 because if f of sigma equals to 1, then we just know that sigma of 2 equals to 2, sigma of 3 equals to 3, and so on up to sigma of n equals to n. And then, of course, since sigma is a bijection, we have to send 1 to 1. So sigma of 1 equals to 1. And then f of sigma is 0. So this number cannot equal to 1, and it just means when you have two elements, you cannot mess up. So either they are both exchanging each other, and it is a transposition, or not. Okay, so sigma cannot equal to 1, sigma cannot equal to 0, and of course, if f of sigma equals to 2, it means that sigma of 3 equals to 3, and so on, sigma of n equals to n, but sigma of 1 is not equal to 1, and sigma of 2 is not equal to 2. So since it's a bijection, of course, sigma of 1 equals to 2, and sigma of 2 equals to 1, and so sigma is just a transposition 1, 2, and this presents it as a product of transpositions. So basically, if this f of sigma is 0, 1, 2, we are done. And so let's just prove that now we take the counterexample with the smallest f of sigma, and so if it is very small, we are done. Otherwise, let's show it's not actually the smallest counterexample. So let me do that. Okay, so let's continue the proof. So now let's let sigma be a counterexample with the minimal f of sigma. So there is finite number of permutations, so definitely there is one with a minimal value of this f of sigma parameter. So then what we know that 1 goes to something, 2 goes to something, f of sigma goes to something which is not f of sigma, and then everything else is just the same. So n goes to n, and n minus 1 goes to n minus 1. Everything after f of sigma goes to itself. So then let's take, suppose this f of sigma equals to k. So let's just take a permutation sigma. Let's take tau equal to sigma. And let's first do sigma, and then exchange k and sigma of k. So that's a transposition, and this is sigma. And then, of course, we know that if you take tau of I, this equals to I for I bigger or equals than f of sigma. Why? Because this permutation doesn't do anything, because after f of sigma everything stays fixed, and we know that f of sigma has to go to something lower. So if this is k, then we know that sigma of k is actually strictly less than k, because we know that it is a bijection, so k cannot go anywhere here because all elements here already have preimages. So it means that sigma of k is less than k, and so we know that so this is k, and so we know that this permutation fixes everything except k and sigma of k, so definitely everything after k. So moreover, if you take tau of k, then of course it just equals to sigma of k, sends it, so this is k sigma of k. Sorry, that's a transposition applied to k. But if you transpose k and sigma of k, k goes to sigma of k. And so sorry, what I wanted to say is that, so if we take tau of k, then it equals to transposition k sigma of k applied to the element sigma of k, but this of course sends it to k, and so tau of k equals to k. So actually tau, if you look at it, it fixes even k goes to k, and k plus 1 goes to k plus 1, and so on. So what it means is that f of tau is actually smaller than f of sigma. But we know that f of sigma is the smallest counterexample, so tau is a product of transpositions. We'll say tau equals to tau 1 to tau k, tau l, a bunch of transpositions. But then we know that then of course sigma equals to the transposition k sigma of k inverse, and then we need to multiply on all this stuff. But of course, let me call this one tau 0. So we know that any transposition squared is equal to 1, so it means that the inverse of a transposition is the same transposition. So tau is tau 0, tau 1, tau k. So sigma is a product of transpositions. And we are done. Yay. So that's the proof. I know it's a little involved, but if you think about what you actually do, so again, you have your permutation, and you just see, okay, doesn't go to n? If yes, then go to n minus 1. Doesn't minus 1 go to n minus 1? If yes, go to a lower number. If no, if n minus 1 goes to I, let's just exchange I with n minus 1 and just multiply our permutation on this composition and substitute it with this one. And now we know that our new permutation sends n minus 1 to n minus 1 and just proceed us like that. So in this way we get our permutation as a product of transpositions. But there is another way to think about it. You can just, let me just very briefly say, so if you take this diagram, which I talked about before, and draw these arrows, which I talked about before, so let me take some permutation, say, I don't know, this one. So then you can just go along this diagram, like scan it, and see what it does. So you move until the first, so you move from top down below until you see a crossing. When you see a crossing, you just write down a transposition. So for instance, here 4, 5. So then you go down later and you see transposition 1, 2, and you write that. Then you see transposition 3, 4, and you do that. Sorry, yes, 3, 4, and you do that, and so on. And eventually you just write your permutation as a product of transpositions. So if you just write a transposition as soon as two arrows intersect, you will get this product. But I don't want to go into all details of this geometric argument. Probably for the first time, this more involved inductive argument is actually more looks more rigorous. Perfect. Okay.